University of Groningen, or rather Groningen, in the Netherlands. After that, he moved to the United States in the University of Maryland to do his postdoc, and he was there for 4 years from 2008 to 2012. And then he joined National yeah, yes. The change from the massive physical laboratory, right? From 2012 to 2019, before joining here as an associate professor in and he loves laser cooling and trapping of ions and atoms. Okay, so
Okay, thank you so much for joining us.
yes.
Okay, so good afternoon to everyone. So I am going to talk about things that we are doing in the PQM-lab, and that is basically we are building high precision, high sensitivity instruments to use it for sensing at very accurate levels. And one of the backbone of these things is optical clock, and I will come into that. So what you see here is rate change is actually data. I will come to that part. So why it is not changing? Why all the instrumentation people start okay. So basically this represent quantum measurement lab that I established at IUCAA, and this lab started its first functioning from August 2021. And this is a more or less recent picture what you see inside the lab, and the lab was majorly developed during the COVID period of time. The goals of these labs are quantum metrology, and quantum metrology can be done in various fields. In our case, we do the quantum metrology using photons, and these photons are very stable. Stability of the energy for like 60, 70 on that or that. And here are the monochromatic fields. 99 of the photons are like hundreds of milliamps. So we do photonic quantum metrology basically. And then we use what metrology. Metrology means you do measurements which have high grade of accuracy, and then everything has to be traceable and systematic has to be started. I mean, if you do any measurement for system statistics, generally for any measurement people do statistics, but for metrology systematics is the most important. The measurement is limited by system. And quantum metrology will use any quantum measurement to start. So we also do sensing using this kind of photons. And finally, our goal, which we are not doing right now, but in the future, is to study science using these instruments. Right now, we are building the instruments. You see here the people who actually work in these are the former people who contributed significantly, and these are my collaborators to experiment as well as for the theory. So before actually I go into the deeper into the instrumentation, just briefly at a glance, I need to tell you what we need to know these things. But you see here, this is an optical spectra coming out of the frequency comb. We don't go into detail what frequency comb, frequency, etc. You can see the input sound up, top, and out, which at equivalent space, which looks like a comb. So I can use comb. And this looks like, let's say, these ones with many outputs. But if you take any comb output, then they can have this kind of oscillations, instability, and they can also do these things. So there are two kinds of oscillations. So that's not acceptable for our applications. So you have to stabilize this entire spectrum. So what you see here, this is the output, main output, and this is the frequency double output of this part. So first, what we have to do with difference, which is stability of resonator. We stabilize the resonator, take that as a difference, then stabilize this entire spectrum. And what will happen? These oscillations will stop. But still, I have these oscillations. Then for that, we take the reference from RF optic or RF clock, and this spacing between outputs are in RF domain, like 80 to 200 megahertz. So we take the 10 megahertz output from its rubidium or cesium clock, and then enhance it to 80 or 200 volt, and then stabilize that frequency. Then you have basically stop these oscillations as well as these oscillations. You have a very participate. Should clearly explain why this is instability. For anything you get, yeah, so this happens from, then you have to understand how this is derived. First of all, this part requires also commercial. What do? You basically take a femtosecond out. You shorten the paths weight of the laser and then pass it here media indigo. And if you sort its time scale, then it will broaden the frequencies. Right? That's what you see in frequency scaling for. Passes through a nonlinear crystal. And crystal has its crystal property, temperature fluctuations, and all these things, and that's why it's instable. You cannot do that anything. You can make this crystal stable enough to get to 10 to the power minus 14 level of stability, etc. But that's also instable for us. Okay. So then you have siblings, these things, but then still it will have symmetry. This group is very strong. But it will have a break. What we have when atomic universe, you can either take neutral atoms, then optical lattice, or you can take ions. And two and laser spectroscopy of one of the important types of phenomena that like really narrow transitions. Now it is not going to diagonal transitions, now for transition, it will be a minor. And now it doesn't be there. Atom doesn't change, doesn't do any aging or anything. But stop things to become very, very stable. Stop. What do you do between them? In between what? Atomic lines are not taking space like what yeah, so that's what you see here. So this is suppose if I fix one thing here, yeah, and one in the other side. Okay, so with some outside, what prevents what ensures that this is not there in universal range? Because what you say, because this is the same part, which is the spacing between the gaps, that is fixed by the alpha, which is like 10 megahertz output of an alpha, which you multiply with some electronic multiplier, and then fix it with this, let's say it's 200 megahertz, multiply with 20, and then fix this 200 megahertz. So basically, you fix these oscillations, you fix these oscillations, then you also fix this load. No, and then clock give you some transitions in your table lines are particular transition for intervals. And even how you transition. So for an clock, you have a transition. And here on it, no transition. So for example, for ytterbium-ion, if you take the clock transition at 467 nano. So we take a laser, send it to the ytterbium-ion, stable laser, etc. Measure this 400, send the clock transition at 467 nanometer, and that gives me atomic reference. In that transition and frequency of what was the output of the frequency curve. This is not exactly matching with this output. This is at some different, which is like let's say 20, 40 megahertz, and that is fixed. I fix that thing. But keep it at 40 megahertz away, like frequency curve from the 40 megahertz, let's say away from where. And that's how this is fixed. Is that clear? So in that way, you use different atomic transitions to fix the frequency. I need only one atomic reference to fix the entire, because remaining everything is fixed. I have already fixed it. And so by actions, I am basically fixing this load rate, which is around 100 megahertz per second mass. And it's so fixing that. And taking last one. That's the second verse. The atom that you have targeted to this, it will have its own broadening. Right? So yeah, so that's why I say this is not a relative dipole transition. Dipole transition has broadening on the bits of megahertz. We use optimal transitions, highly coordinated. Finally, this 10 nanohertz cannot reach to that level, but we can reach to 100 megahertz. So broadening in this case is our case 100, so which is over 10 to the power 15 hertz, which is the optical transition will reach 100 megahertz. That is what it is. So what it is. And okay. Now, so far so good. So we have everything in the lab, but that's not so much useful. It may be useful for something. Now you to transfer this knowledge to another lab, maybe experimenting in a different place. So for that, I need to forward that part in the I need to measure, I need to know what is that atomic frequency. It's inside the atom. We know what is exactly that frequency. That I can do by properties of the optical frequency. Because optical frequency comes two fixed things now. One is this alpha, which is this between two frequency out repetition rate, and this H0 from where it starts, and I can count how many hits I am having. So with this CS happens gain infrared and zero, and I measured this separation between these two frequencies. This is by measurement I can extract what is exactly this clock frequency with really high accuracy and so on. So now once I have that, I can pass this information to far away, maybe hundreds of kilometers away or maybe kilometers away. I have to send it through the optical fiber, and optical transmits 1550 for longer, very long lengths. And so I have to stabilize the length of the but I have very phase coherent photons once I send it through the optical fiber length changes. So on the other end of the fiber, I will still get broadening because of the phase length change, which introduces phase change and d phi by dt is delta mu. So that will bring broadening, which is not acceptable because then when my entire experiment doesn't make any sense. So I have to like stabilize the optical. So you know now what are the things we need to do to establish this experiment. There are only few things which we buy. Majority of the things we actually have to develop in the lab. Why transmit you can have the class home there itself, the value of it. But then you have to have another see, okay, fine. I'll come to that. Can you hold this question? I'll exactly come to that. Okay, so now why do we do an obstacle clock and time clock? Because it is optical. We time clock you anything with optical astronomical instrumentation. Even GW is also lying with an optical camera. And then also okay. But on the other hand, yeah, uh, the science goes for doing this optical clock is basically similar to what science called the optical astronomy or observational astronomy does. So that is looking into symmetry breakings or looking into variations in the fundamental constants. Geometric measurement, even if you have a very rapid clock, it can give you over the time, which is like 10 to the power minus 19 to exchange clock. The other usefulness of the clock is like linear frequency, meteorology, time stamping, etc. But that is not what we are because that's a funded of the meteorology institutes like anywhere. So we are not doing that. So in parallel to that, so now coming back to your question, Anand, what why I mean there are few arcane optical clock activities in India. India is very just about optical clock for their time frequency lab is meteorology for that. In Pune, India, we also in uncertainty they are developing a strong CM atomic clock. In Tirupati or in Swarma, they are developing transportable optical. This clock will not be that accurate with transport. So once you build a clock, you can have a very good clock, but how to measure its performance? Another clock, it's a similar level of sensitivity. And you need at least three such clocks. This is what cheap user has. With two clocks, you cannot say that which one is in. So with at least three clocks, when you get 3 point correlation measurement, and with this you can establish that which clock is more stable or less stable. For that, just bringing one clock at APL or one clock into RS doesn't help. We have at least some critical numbers which has to be finally connected with the phase stabilized optical fibers. And I want to make very sure, like this is a very important thing. Just making clock will be a service. So what is quite good. Yeah, it can be. Yeah, it can be. But first of all, different physics interest in them. If you have regulation one and neither they may say that they are interested in fundamental science, but they are neither is physics. On the other hand, you can see that should be always something disaster happening. And if you have three clocks in three different locations for these fundamental solutions, is not a big measurement. Correlations can be much better, right? Same things with LIGO, like you have to have like geographically separated just for clocks also can have geographically separated groups, then you can actually do all the science at random dimensions. If you turn off that mic, I can get see which one. I think that is the one. Somewhere that feedback coming. This is all.
So how big is the clock? Is it as big as a full optical table?
It's like two optical tables.
So it's
In size is 3 meter by 1 meters.
and then their ones are also big.
Yeah, yeah. So these three clocks are all big clocks. They are best clock, and we expect that it should reach to a stability of for minus 18 level or even better in the future. But they are trying to develop more compact now, 319 inch like server lines. Yeah, but then you have to pay with the stability or performance. They are aiming to get for minus 50, which is very good for many practical, but not for science. Okay, but other than that, also why we develop, why we thought see the light media, both these are the science, but these are the technology what you need. Develop skills. That was what sort of this you can develop all this human resource with skills in electronics, optics, laser control systems, and very high-end simulations while we are building the optical. Basically, at the end of the day, we also deal with laser, optics, vacuum, electronics, control. In life, we are very, very different. But to start with, to get these skills, one can start with this kind of. And that's what it was thought of at the beginning. And that's what we are doing. So addition to that, some of the technologies that is because not I will come to the later part of my talk. They are very, very useful for the journalism of the future journalism. So that is what I also doing. Come to those who need to. Okay. Now I am having to go deeper into the technical. This talk will be more technical. So as I said, for all practical purpose, basically we have to generate as well as disseminate ultra-stable near and monochromatic signals. And ultra-stable is phase and frequency. These two quantities we have to state that. And the photons, we choose at 1550 nanometer because that is transportable so enough for very long. That's what I say. Now, to start with, we just start with a commercial laser. And if you take a very good quality commercial laser, this laser will have this kind of features. They will have critical alarm indication, which is plotted here. So on the order of 10 to the power minus 7. Alarm indication, is, from the name itself, you can see that it's measured deviation. And lower the number is, better is the power. And typical like sort of drift is about 100 megahertz or even watts at 1 second. So that means you can put these numbers into this formula delta nu by nu and you can get delta nu by nu on the order of 10 to the power 7, which is then just a laser to start. And we want to bring it down to this level, 10 to the power minus 16 level. So to give you an idea of this 10 to the power minus 7 and 10 to the power minus 16, these two numbers, 10 to the power minus 7 means if you take arch diameter as a length, you have to control the diameter to be the length of an hockey stick, which is about 1. Whereas 10 to the power minus 16 is arch diameter, you have to stabilize this 12,700 kilometer with a length which is dimension of a year. That is like nano. That is the difference. So that in between this requires lots of instrumentation to go from that level to this. Okay, and that is what is basically you have to bring this 100 megahertz to 100 gigahertz level. Then only you can get 10 to the power minus 15 or 16 level of that. What do we do? What we start with, we first build a reference optical resonator, which is fabricator cavity. And we stabilize the length of the fabricator cavity like 10 to the power minus 16 or 17 level. So that is a heroic effort. This is not a normal fabricator cavity. We have to stabilize. This is like a 300 millimeter cavity, and we have to stabilize the length of the cavity at that level so that net stability is transferred to the laser to stabilize the laser at that stage. So that means you have to isolate this cavity from everything, from acoustic vibrations, from normal surface vibrations, temperature fluctuations, conventions, everything. So let's say you do these things, and then the laser this anti-radiation would be laser to be 10 to the power minus 16 level. So it works in optical filter. So you can narrow down the diameter of the laser from hundreds of kilowatts to less than 1 part. So what you have to do to build this kind of like very specific fabricator cavity? Okay, by the way, one more thing. So if I go back to this picture, um, what you see that we need several of the locking electronics to lock several of the laser frequencies that all of them are not stored here. Counted, we total need 12 locking electronics. Frequency stabilization of all the lasers and intensity stabilization of. And if I buy all these electronics, it costs tens of lakhs for each of them. So we thought, why don't we build the electronics ourselves? And that is what you see here. This is all digital developed, we call it soft box. These instruments have two channels. These simultaneously controls or locks two different laser frequency or intensity or even temperature. This is completely digital. It's not only servo electronics, but servo it is RF lock-in amplifier. You can also monitor unit all together, which is a touchscreen display and also controllable from a remote place, like from a remote. And you see that this is a very low noise electronics. It's like only 13.2 nanometer per square meter noise density. The world best thing is about 5 nanometer. So we are very close to the best one and things are very fine for all for because all the parameters are very, very good than compared to what we need. And these are few features of these things. Preparation. Okay. Now for building the cavity, we have to start with designing the cavity. And this designing is just not a SolidWorks 3D drawing, engineering drawing. We have to do a lot of simulations, estimations to understand what exactly we want to design. So major difference between bringing it from from -9 to -16 or so is the design of the cavity. It's the design parameters isolation from the different noise sources. And you have to understand what are the possible noise sources. And you have to make sure you have to come up with ideas how you can isolate from. It will be more clear if I perfect this way. So we have to optimize the length of the cavity. Like it's not just a 300 millimeter, but we have to see where the power in the higher order modes are minimum, and there is some optimization. It's like for us, say 73.3 millimeters. So it's not exactly some. Between okay. Then you have to see like what are the modes you have fixed there. Right? They're all fixed. This is an influence, so I'm not going to change it. It's inside. Then you have to see what are the mode spectrum of the design cavity. Radiation resistance is not that important for a work with very low power, but it is very important for line. You are designing the cavity with stability region. There is a phase diagram for the cavity for any stable change. And what to do it in the edge of the phase diagram or middle of the phase diagram, you have to choose depending on what is your application solution. So we did all these things, and not only that, we also made a software so that anybody basically can just type in their numbers and get these optical parameters immediately for any solution. It's not published in web, but right now we have a land published in web so that everybody can. Then the second part is thermomechanical, which gives the all the instability. And these are like shading from the temperature vibrations, shading from the temperature fluctuations, from vibrations, same point deformations, even the chief fluctuations, like let's say the cavity is in TI hot, Mumbai, and you have high tide and low tide. Change the deformations into the cavity and shift everything. Or not, that's not the case. But we have to think that how to isolate all this. Slow crossing temperature of the cavity, like where effective coefficient the temperature expansion is very close, not quite very minimal, like nearly. Then it's something we have to do analytically also. Brownian noise, we have to calculate pressure, what kind of vacuum level do we need, and we have to measure what we have to know that what is the effective coefficient of thermal expansion of your cavity, which is depends on the design parameters. We have to choose what materials do we want to use for making these spacers and mirrors. For example, we found out that ULE as a spacer and fused silica as a mirror substrate is the best combination. We have done all of these things, and these design requirement also needs pencil or specific. Yeah, yeah, so this I'm just going to be plot. So this is like we will do everything proper. Then we think that cavity will be having known 100 millihertz per second drift. And that is why you need big clock, like clock transmission to correct that. I don't think we can do better than that. and that is defined by property of the material, aging of the material. Cannot do it.
Can you explain what this Brownian noise does?
So Brownian noise
Basically, the phase the change.
no, Brownian noise is again like Brownian motion of the particle
Inside the case.
not inside the inside the cavity. So cavity has a mirror. Mirror has a coating for the reflecting. The materials is a very right? For any temperature, then you have Brownian motions. If you increase the temperature, Brownian motions will be more. To decrease the temperature, the Brownian motions will be less. For us, this cavity is in room temperature. If you want to do better than that,
Where does it affect? How does it affect the study?
how the Brownian noise that will change the cavity length. That's what the only will change the cavity length.
We have the how do we say why can I see?
It's a thin film, right?
Mention somewhere that radiation pressure is not important.
No, radiation pressure is not there.
Only then I can see the separation between these two galaxies.
Yeah.
This motion is random. Next thing is scattering.
No, it's not scattering. It's a random motion.
Now, infractional photon is what you
It's different.
if there is a random motion occurring here, I don't you know only about the place where you're sparking.
No, what is what? Like that's what I think. Yes, that's scattering. And there, effective length will fluctuate. And see, we are talking about fluctuations of the time. Again, molecule size is in size of micrometer or something, maybe on the nanometer. Yeah.
Hey, wait. I have to I have to take the distance between them. I have to displace them in the direction of the photon. Right?
You can do any directions. You can do any directions like
In directions. So random motion, how does it changes the length in this? This I don't understand.
so. These random motions will make this thin film like will basically oscillate this thing.
Oh, okay, you are saying that the thickness of the film will be a constant. Is that what it is?
Kind of, but thickness is more related to the radiation because there you are impinging some energy and that is
Instead of saying the surface where the surface is stopping the
yes, that's one. Yeah. So you are doing the finite element finite sequence. Yes, we do. We do. And what?
I know you have to just push it away.
Yeah,
Yeah. Double is your
lots of times. So it's some
no, just to connection to the
team to let us I think the loose connection will be with the
connection.
loose connection. Just reconnect. Just open and reconnect. No,
See,
from the medical and reconnect.
we just start it.
You open from the computer right side before you open it from the computer. They try to connect. So that the computer forces to go for a display I mean, you have to.
Yeah.
Hospital vacancy.
Computer science
Yeah, no, opportunity now. You can be our Yes.
start again. You didn't go into sleep, right? You were thinking.
I know it went into sleep while talking, and then it was something has to be told. Yes, okay, why not? Something that is.
You'll do only the HPC.
Not 1 second.
You wait, it is starting. Yes, it is starting.
No, I'm just checking whether the display is detected here or not.
And that thing is not started. Oh.
See the displays are showing up here or not? No, you don't detect it. See, there is no display here.
Try that other machine. Hey, this is not there.
No. Please say, can you start with? No, that before this thing comes, you already see the new specific electronically responsible. Please write me. Not this are all experience. Responsibility. Yes, most of this you can come. When you see the showing up here. So, yeah, the next well, that's great. Great, I know. Sure. Now, watch this. This one. Anand Swan and cannot go through all this. It is supposed to, but it is not very. What? One second. You maybe the next one. Very much problem. नहीं आ रहा है. Here it is actually detected. That is fine. नहीं दूसरा मशीन में लगा के देखना. हाँ, नहीं no, you log in into Zoom or okay, but Zoom में तो login है. That's fine. That is fine. We just not in that link that is built then he can do it from. No problem. I need to office it. It's not working. I'm trying I'm trying to get replace this input. No, no, but that one is very good. Let's try that. One is very good. विजय कनेक्टर से करना है और विजय का कनेक्ट ठीक चल रहा था तो वो दिन में क्या क्या किया है फोटोन को इतना एक है yeah, I just I can say we want to use Subhadeep performance. So now, so is there? Is anyone there on? I just stop sharing the thing. Okay, here. So this our usual one has. Okay, so can you minimize? Yeah, just minimize this. The nobody is Zoom, right? So we should stop with you. Okay. Very well. Don't stop it. No, which no, अभी नहीं stop it. Just stop it. So now what you see here, like these are the value. If you look at just normal cavity, not the very stable one, just normal cavity is what we use typically in the lab. And these are some parameters. Length, I have kept the same as our length of the cavity, but the stability, finesse, all these things are for normal cavity. If the mode spectrum will change, the mode will oscillate because it's a very normal. So these are the typical vibration modes of a cavity. And if you take a very ultra stable cavity with very high finesse, with very high large these things, you look into these numbers, which basically delta L by a fractional stability of finesse. They are in on the order of 10 to the power minus 15 or 2 at 1 G, and we have much more smaller G. And as we design all these things in such a way that 10 to the power minus 16 level of delta by L for all hydrogen modes and etc. And now if I look into cavity, that is click on the surface. First, it is okay, now this is also actually a simulated video, but since it's very, very stable, none of these things you can see visibly something oscillate. So for this, we have basically came up with a new method, new simulation method to estimate this kind of vibration instability. And what we do, like we take some known geometry, which is already published results and etc. for their design. We take that as a guinea pig and we simulate their parameters and then cross check whether we are getting the similar parameters or not. That's to make sure that what we are doing is doing a correct. And you see what we found out basically their experimental result is 5.9 times 10 to the power minus 10 level of stability at 1G. We have simulated result this is 2.5 and 2 minus 11, which is quite different compared to what they observed in X. What is the C? Huh? What is the C 1G? This is 9.8 meter per second. Wow, the accidents. Then we tried to different other methods and we found out one particular method which actually affects the result they are getting. That's why we actually found whatever we got established, we mentioned an experimentally measured result. When become more. What what these are like experience there. So very important. I think movement is research paper. What you give one acceleration only around the three directions. Method two, you give accelerations in all three directions. One direction means where the gravity is more sensitive. That and in second method you give acceleration to three directions. But then they don't do modal analysis. In method three, we do the modal analysis, we see what are the resonant mode frequencies. And in method 3, we actually see that what are the frequencies more important depending on what are the vibration, isolation, vibration frequencies, and etc. on start list. And then couple those frequencies and see what is the with base stability. And you see that this we have developed this method, and that is actually more accurate. It is nobody else has done.
No, this I don't. Maybe I'm missing the point. If I get 4.5 to the minus 11, I should be happy with that compared to 5.84 to the minus 10. I'm missing the point. What are you trying?
But the point is, this is not experimentally verified result. The experimental result is 10 to the power minus 10. I am simulating something which is inaccurate. So I want to simulate something which is actually accurate, and so that I can.
No, but you have now added something which brings to the same value. How does it prove that that is right?
Yeah, so that's what is their experimental value.
That's what I'm just saying that you can get the experimental value because of something else also.
No. If do what? Yeah, this is experimental. In the real world, we develop the method and develop and select the instrument before they are hanging. These two numbers match. But simulation
saying is that unique. For example, if you so like use G in one direction, then you will get this. Don't use the number. For an example, does it prove that that is the only reason why the sensitivity is minus 5, that is minus 10?
okay, but
Point out some other things which you would miss.
see, there are only three relations.
And only G, there is no other effect in all the others.
So acceleration is measured in the unit of G. It's not G. He's saying that it is acceleration only for acceleration is measured in the unit of G. That's the typical one.
I want to say that you are using one effect that gives you the accuracy of the so that is the most important.
Because this is also for that effect now. This is not for the total instead. That is also only for that vibration sensitivity. That's why it is vibration sensitivity. So the thermal sensitivity and all this people. This is only for that. So the second important thing is the temperature stability. And there, like what we want to do, we are considering the cavity from the environment temperature. The gas temperature fluctuations is 1 degree centigrade. And if that comes to the cavity, then it will be killed. There is a thermal expansion contraction. So we have to isolate. The way it can happen, the cavity is typically three ways: conduction, convection, radiation. But now this conduction is very minimum because everything there are only 3 points where it's connected to the this is the cavity. There are two salmon seeds and 4 points in each layers, which is connected to the cavity. So there is very small surface area through which temperature can propel. Convection is also negligible because it is under very high vacuum. There are very few particles inside. Convection is very minimal. The most important thing is radiation. And for radiation, what is the radiation? We have to decrease the surface area of the inside layers. And we do mirror policy. We are kind of polishing of all these layers to reduce the surface area by factor of 200. So radiation is suppressed in that. And in addition to that, we have these three layers. So the connectivity time scale, 1 degree centigrade temperature propagates inside the cavity takes 15 days, 15 to 20 days. If I have a 1 degree centigrade temperature in the outside, it will take 15 to 20 days to make a 1 degree centigrade temperature inside of the cavity. I have an active feedback loop which works much faster, in less than 3 times scale, which corrects. So when you get very good stability, temperature stability, and the temperature stability, what I need is few millimeters. So what you see here, this is the coefficient of thermal expansion at temperature dependence, where at what particular temperature it has a very small value, which we call 0 very close to zero temperature coefficient of thermal expansion. If you zoom it up, then it looks like that, and from the minimum value, if I go at plus minus 3 to 4 millikelvin, I get order of magnitude difference. So that means I have to stabilize this feedback loop temperature by a few millikelvins level. And that is what also Sampango is developed almost this temperature control of feedback loop. And it's not one thing, we are testing it right now. And we are very sure that we can do it and we can.
So in this case, you would do some kind of feed forward, just the response is very small. So you predict what it would be, then you apply the correction.
What we do, we predict means we measure. And we have the calibrated thermistors, 1, 4, 5, to 6, the different parts of the thing. Measure their resistance, make a differential circuit. With one thing, we give a set point voltage, which is very ultra precise voltage, stable voltage, and we measure the voltage from the thermistor and make this differential.
So this is the feed, not feedback.
This is a feedback.
Feedback. Because the values that you're trying to measure are very small. So how well accurately are you able to measure?
Yeah. So see, for this one, we really don't need to. We don't need to do this feedback at millikelvin, because you know there are 3 layers and it takes 50 days. So even if it is slightly worse than 3 millikelvin, it won't be problem because it won't propagate to this inside the contact. Okay.
This is done at outer part of where this
So this temperature
sensor will sit where.
the sensor will sit in our
Give the feedback to
maximum surface. So that is the next thing. I mean, maybe I can just show you. So this is the changing timeline of our entire cavity setup. So here you see this is the diagonal chamber, and then there are 3 layers. Cavity is sitting inside, and this is all optics. This is input center thing on vibration isolation. The first level of vibration isolation is high. It's again sitting on some composite materials on the surface, on that surface, and then there is an active vibration isolation. This entire galaxy is covered by what you see here. There is an acoustic shading. This white thing what you see here, this is covered entirely. They have removed it to take the picture. This acoustic shading. And inside of that, then there is this box, which is again there is a 2 layers of aluminum, which is separated by some insulator material. The aluminum gives homogeneous temperature distribution, and the insulator gives again some time constant inside. This is the second layer. And then there are these 3 sophisticated layers of thermal insulations, and that gives very high long time constant that you can really do it every time. But see, here you are sensitive to the differential layer, right? So since both are the rigid structure, I mean, do you need so much of isolation? Meaning compared to the so much of thermal isolation or not power? Few isolation, vibration isolation. Because compared to the thermal isolation, that will be much thermal fluctuations are much larger than the. Yeah, exactly, and that will come to the next slide. You will get in a comparison. So I mean, we have designed all these things and we are putting these things together. Right? There is the parts right now. Basically, now we are doing
exactly. Exercise where I was asked. And that goes into designing this vibration. The number you brought to the.
Yeah. So we first make sure that what we are doing is correct and apply our. So essentially, this is our unit. Now we establish our confidence with that. Say, okay, now whatever we are designing is design parameters are.
Your cavity will be very different from
cavity. Yeah. So now what Pandita is asking, so these are the different noise or instability parameters that we have calculated. So finally, basically everything will be limited by the Brownian noise. That is the blue line what you see here. And this black one actually sum of all these noise from the temperature fluctuation. As you have correctly pointed out, temperature is much more sensitive, and then all the other parameters. So at room temperature cavity, we are limited by the Brownian noise. The next level will be raising for everything in the cryo at primary temperature, but that is a much more complex systems. We are not going into that direction at this moment. And this is a global comparison of our cavity with all other similar cavities in the world. These blue ones are the cryogenic cavities. So they of course should have much better performance because Brownian noise is much more. But for the room temperature cavities, we see that our results, design parameter results are very good compared to world based ranking. And we hope that we'll reach that.
So these world-based cavities are they measured parameters?
No,
They are not designed parameters.
no. How they are doing it for us.
Right. So how were their design parameter at the time when they designed it? I mean, because you are comparing with the design parameter.
For our method, this is design. For them, this is the result.
So how different it is than their design parameter and the major parameter?
That's a good point. I don't know. I don't know what my friends line that.
Isn't that the one who's on the table? That's what you
One is
No, this is not. That is not. That is building environment. That is UK. That.
And sorry, just a related question. So if it's a design parameter, so what could be expected deviation in terms of the realistic parameter?
That
Yeah, that's why.
that we can only say once we measure, right? Yeah, but that it's very difficult to give any comment at this moment because it's like in Indian roads, if you have the red light, this is just a suggestion that you follow. You got to follow. So we can only measure it at Indian 60
What that means?
How can you also simulation? This is our simulation. Our simulation. So this result, this number comes from this simulation.
that's very too far.
Yeah. So these one is with direct, considering dielectric mirror. The other one is crystalline mirror. That is a new type of mirror, which is crystalline mirror. The green one is dielectric mirror. We are not going for the crystalline mirror because we figured out at room temperature they have birefluence problem. They are like each mirror is fluorescence. No quantum. If we don't make a cryogenic cavity, there is no need to go to the crystalline mirror. So likely you should compare with the green one and
No, I think that okay, coming back to the original thing that instead of putting so much effort for the vibration acceleration, because it was not this thing because it's a rigid cavity, no, it's a not suspended.
no, I think
Why you not go for actually lower temperature so that that green thing comes.
see, one thing is spending time in front of computer, one thing is criticality in doing these things. If you want to put, let's do this. If you put entire cavity in the cryogenic, that is altogether a completely different level of complication. You have to bring light inside the cryogenic. Yeah, so that is technically much more complex. I can do simulations if with a student anything.
No, I don't know how it scales with temperature. Like you know what?
It scales linearly. It scales linearly.
He does the realization. You will know what is getting great. How
It scales linear. Temperature, the Gaussian noise. Yeah.
Fine, go ahead. I mean, how much the guard come down? That's getting.
Yeah, I mean, one can do the simulation, but since we are not doing cryogenic and we have decided, I don't see why. I mean, if I have a enough instances,
No, I was asked. Fine, later. Because if there is a technological like bottleneck, you cannot reduce the temperature.
it's one one. Okay. Now, if I do everything correct, basically, then I will suppress. I will need to this for sort of 16 other mechanism, but due to the material property of the cavity, they will slowly drift. This drift rate is around, as I said, 100 millihertz per second or on that. And to stop that, this is what result of this is that 100 millihertz. So, it's a millihertz per second, 100 millihertz. And that we have to suppress, and for that suppression, we have to have this atomic reference. And for us, this is an ytterbium-ion, and we excite the octupole transition of the precision level spectroscopy and give a feedback to correct that very slow drift. Why we choose ytterbium? The choice of ytterbium comes from the science interest. Ytterbium has two clock transitions, one that 467 nanometer and octopole transition. And another one is quadrupole transition at 435 nanometer. These are not dipole. Quadrupole and octupole transition, that means they are very narrow in their line width and these are clock transition. And these transitions have a differential sensitivity on alpha variations, that means slopes are different, what we see here. So if I make a clock of ytterbium, same ytterbium-ion at two different wavelengths, in fact, this one string can measure the alpha variations to some upper band of this. That is a very unique feature of ytterbium-ion. That was the reason why we choose ytterbium-ion. Some other technical advantage also, I'm not.
Pune and Tirupati, they did not have ytterbium.
No, I said Pune is strontium and Tirupati is calcium.
So they have different sizes in cubes.
Calcium ion for transportable clock at Tirupati, that is a much simpler atomic system. So for transportable system, that is much easier. And anyhow, you are not going to 10 to the power minus 18. So that's an easy thing. For strontium at ISA, I do not know what is the changing system. But maybe they also want to go for commercialized. Okay, so for laser systems, I of course need the two laser systems at the clock wavelength, but for production of the ion, helium atom, this is done with photoionization technique. I need two photons, one at 399 nanometer and another one at 669 nanometer, to strip out one valence electron, one of the valence electron from helium at ytterbium ion. And then for laser cooling, I need additional three lasers, that's 369, 935, and 760 nanometer to make a closed transistors. And these lasers right now we do not have, but the clock transition lasers we have. The ion trap itself is a very difficult thing. We took us 3 years to develop this thing, to collaborate it with Optical and another. Why? This is a very precision ion trap. The size of the ion trap is only this much. There are many components within this size. So machining of that, designing was not so difficult. But machining in India, who can machine these things, that was a very like long exercise. When finally this is developed, I'm seeing a picture from RRI from us. They have already tested this magnitude for their calcium system. They want to do some quantum derivatives. But you see that they are able to trap ions very nicely and etc. And this is a collaborative work. We have decided to keep this ion trap to other implants like origin and also CSI and have an MOU together that this joint development is used for another.
So who machined it for you?
CMTI in Bangalore. There are two parts. There are some ceramic parts and there is some metallic parts. What you see here, this is the metal ceramic part. You see here this white ones. It is very small in diameter. Ceramic part is made by SS Ceramics from Bangalore.
They have that precision to do it.
It took us 1 year to get them. And then this metallic part is CMTI Bangalore. It's finally assembled in RNA because we have high precision microscope for material science functions, etc. And we're going to use one of these stuff.
So one of the ytterbium also is this one.
Ytterbium not long. They started with atom. It is not atom spectroscopy. This is only spectroscopy, but not long. And there is only one published paper on spectroscopy. That's my not, but that is also ytterbium. Okay, but on the other hand, to track these things, we need few other things, atomic model and radical resonator to try the trap and extract those we have. Actually, I developed it during NPL days, and others is also with the same designs in etc. So that's how.
So this plot, what is it? Plots telling?
This is so this is like electrode off. Then you don't have ions. This is the some what you see. Then you switch on electrode, then you get the chapter and the speakers.
So the difference is so small. You that it is
Not only few ions. It's like not a million ions. It's like 3 or 4. Okay. Another important thing for the design parameter is material choice of the ions. So we are very much for clock use, we are very much concerned about the ion heating because ion heating gives black body radiations. And the black body radiation scales with this. Black body is like electrical component of the black body. This is the sort of formula and it scales as T to the power 4. If we choose the right material versus it's a not so right material but very good vacuum compatible and obviously we can see the height of temperature difference around 10 degrees Celsius. And that means this E square has electrical component of the black body will increase by 10 to the power 5. So black body radiation increases at integrated spectrum by 10 to the power 5. That means black body radiation shift of the clock transition will also increase by 10 to the power 5. So right choice of the material is very important and that is completely done at our end. We have done it and gave this input to for receiving this. Choose this property. I'm not going into detail how we do it, but if you want to know, I can say it. Okay. Now, if you have everything, then you have basically excited clock transition and you then have to synthesize the frequency of the clock transition. What frequency are you exciting? That you have to do with the help of the frequency comb. And I already described you like you have to measure the bit low, so in the clock measure one of the frequency P And then with these known properties of number of fields, FR, simplification thing, and offset frequency, you can basically figure out what is the scale universe. Okay, but for that you have to measure this measured value of a bit not frequency, you have to basically do phase noise measurement. Not at the frequency level, but phase noise measurement at very long time. And for that, we have we have to do again three corner hand measurement. Then one is the bit frequency, that is device under this, and we need two reference frequencies. These two reference frequencies has to be very stable, make a very stable count from phase noise measurement, and that we produce ourselves. So this is the electronics we have again produced, digitally synthesized frequency, which you can produce from 10 megahertz to 300 megahertz. And it's a very low noise electronics. Phase noise is minus 120 dB C per hertz. I have compared our result with some, that's a very good commercially available RF synthesizer, and you see the result. So that few companies frequency synthesizer. This green one is our frequency, but our one is very low compared to all the other commercially available. That is also now accepted, and this is also stabilized to be there. So it's a very stable RF source of frequency. It of course does the phase noise measurement purpose we can use it, but for various other purposes we can use this thing. Okay, now everything is done in the lab. We have to send it back, send it through the optical fiber, and we have to stabilize the length of the optical, because that adds the frequency broadening, and like it should be seen like if you have 1 meter fiber, the broadening will be on the order of 10 to the power minus 19. If you have few meter, already goes to 10 to the power minus 17 or 8. So if you have a clock which is 10 to the power minus 18 level of fractional stability, and if you don't stabilize the fiber few meter length, then you don't have any clock. You have to stabilize the length of the fiber better than that length. So that is something the hardware we have completely developed ourselves, called photon C. And this hardware has a photon C. We have trademark for that. Trademark. We have also applied a patent for it. And what you see here, this is now the clock is off, which is oscillating. Frequency on the other end, result frequency on the other end is broader. Clock is switched on, so everything becomes very, very dominant, and we can transmit the fibers almost without any start. And this is the measured Allen radiation of the fibers up 71 kilometer fibers in the spool. And we also have a link fiber between our lab camps building and the K2 building. We also measured it for this deployed. So you see, it seems like very stable as we get longer and longer. It's just increasing stability. Next one. This one.
So, what is the signal that you use to stabilize?
That is the ultra stable narrow linewidth laser stuff, and which that is. And that as a reference we stabilize the fiber. Yeah, so we have a fiber, then let's say light is going through, a small fraction from the other end is sent back to the same fiber. The light which is going back and forth takes twice of the noise from the fiber, and that we compare with the injected fiber. Injected light into the fiber, and even the compensation to 1 hour.
So how you use about if you are sending this compensation is done?
It's almost insecure. It's light. It's going in light speed.
And only once you see
It's not. It's active always. It's not that once you give and then forget.
No, but what do you mean by stabilization and finally?
Stabilization means optical.
I think somebody could check. And I know that while position it may lose the frequency.
Yeah,
You are saying that this gadget will stabilize.
yes.
That's what it is. What exactly would you do?
So, and let's say you have a fiber. So, photons are going in light speed. So, a small fraction of the light from the other end is coming back. So, we analyze the light. And then we measure what is the phase noise, what is there, what is coming back. We measure the phase noise. And then if I give this frequency feedback to an AI stop the modulator and actively correct the phase. So that they say I have this is my starting end, and this is my remote, and this is the A wave. So let's say I want to have this frequency, but what I something like that. So I give it connection so that it comes back, and that will give it the starting end. But if I give it at the starting end, this entire convert stable. You can also do it at the remote end also, but if you do it at this end, because from the end user's perspective, you don't want to do anything at the end user side. You want to do it at the labs.
What you do testing business building that.
Oh, okay, yeah. So we already have a commercial cavity, which is a much smaller unit. So stability is not as good as what we expect for our hand. So we are started using that to develop all the other. While we are building our own cavity, which will have at least an overall technical better.
So this is we are changing the laser people follow the fibers. We are not changing the fiber follow the.
No, we are not changing the fiber column. So we are changing the laser frequency to column. We cannot change the length
Yeah,
of the
but it's not. Yeah, when we are saying that that we are stabilizing the fiber.
yeah. In that sense, it's stabilizing the laser frequency to follow the. Yeah, we cannot do like really changing the length of the fiber. Well, there are some ways, but that's a very slow process, stretching the fiber.
But that's in your case, it means other than because
Only 10% probably, less than 10% is reflected. Remaining 90% is
the
used to.
component reflecting, why can't it introduce noise? That will get to 5%.
Sorry,
The reflecting component.
yeah.
Can it be
It is included. If it is introducing, then
you find some analysis, I don't think it's component. It is the solar.
no, but that is dynamic. You say that I estimate what would be the change, right?
And I'm just saying, you have to decouple the effect coming from fiber with respect to the mechanism which sends that particular signal to you.
That is only a mirror. That is not introducing.
But if you only mirror only was creating all such sorts of problems for the frequency stability, right?
That is but
Routing and other things.
this mirror, whatever instability that mirror is also introduced. That is also measured and correct.
But you are overcorrecting. Now only I should correct what is the effect of the fiber.
No, we are not correct. See, this when we are frequency stabilizing, and that what at the end of the fiber, here my user length is very, very small. So I want to really correct it up to the end where it is good.
That I understand. But when the user takes is going to that's the reason some component you are interested.
But that
frequency is better. You will take it upon.
you are right. In principle, theoretically you are right, but that increase
Practically it is better.
yeah,
Nothing else is zero.
practically is right. But practically this small correction is extremely small compared to whatever. That's not like really.
So you need to say if I take half the length, which will couple to take it full.
Yeah, because it is half the length means more
Instead of 50 meters,
yeah.
I take 100 meters or 300 meters.
Yeah,
So
so
the size is reflecting better. Your connection should stay with enough. Therefore,
it's a linear distance, but it's connection. Yeah. So that's why you have to measure it and correct it. You cannot correct as per your expectation also.
no, sorry. Yeah. So if sigma is the thing you are going to correct, yes, correct is sigma 1. Sigma 2 maybe the thing which comes from the you can ignore it. One sigma 1 is
Fine.
Links reading and by total sigma is taking, ignore that. It is very different from this.
Fine. The sigma 2 is very, very small. We don't.
It's not a mirror, right? It's a cup.
No, at the end it's a Faraday mirror. It's Faraday mirror. It reflects that. So I told you about these 4 different parts which we need to do for building the flow. And all these parts are like ion traps, narrow line with laser frequency phase stabilizations, and ultrastable cavity. So these parts have several other applications other than. And I have listed some of them, and the yellow lines, what actually we are also doing, which we call as an offshoot from our cloud project. And some of them are really connecting to the Chinese club and instrumentation. And in next few slides, I will talk about this. So one thing is uh, distributed acoustic sensing using optical fibers as a sensor. And we call it untrustable, ultra-narrow continuous and laser-based distributed acoustic sensing UAVs. So what you see picture here, this is our PQM-lab and this is this road. And this is the TLC building. There are two fibers going from our lab following this path to the TLC building. This was already deployed. I have just taken it from the outside. One of them we use to send our this highly stable narrow line laser to the PLC and then inject through the other fiber, which is our sensor fiber. This red fiber is stabilized and use the light to the other end and inject it through this yellow fiber, which is just normal fiber. It is sensing any acoustic noise and we are measuring that. This is the optical setup. So the entire optical setup is actually at within the lab, and that's why you have to bring first light to the other end, not have any place to put the experimental setup there. And then from the unit, like TLC, we have just the surrounding unit to send the light. I'm not going to tell unless you want to know about it, how exactly it works. That is what we measure. Okay, this is a or spectral density of the frequency. This is red line, real lines, what we see, these are frequencies, what we measure.
What is it?
What is? Yeah. It is coming. That is the time, and that is the frequency. And these we inject some of these frequencies, what we call markers. And these markers we inject at a particular frequency and known position. And we extract that from our sensor to know that what we are doing is correct. And these are the marker frequencies from 30 Hz to 42 Hz, 41 Hz. In frequencies, and this is the extracted frequencies from the sensor, not the injected. So we extract it very correctly. And just to for linearity check, we couple these frequencies at different lengths and different positions of the fiber, and you see that we are able to take their positions very correct. That way we calibrate our system. We get confidence whatever we are doing, we are doing it correct.
Is the unit wrong here because from here to TLC it's not kilometer, right? So what is actual positioning exactly?
Oh, that is a good question. So TLC to here is about a kilometer. Then to increase the length, the front or at the end, we add fiber spools of 20 kilometers, 100 kilometers, etc. This is only for this linearity check. It's not for sense. Okay, now this is the other frequencies what we have extracted. These are the marker frequencies. We know that they are there and we know their distance. These are all other frequencies what we did. These error bars, what you see, these are actually not error bars in this sense. These are not resolution of our sensitivity, but this is how long this acoustic wave is coupled with the fiber. So what happens, like, let's say this is the fiber and the source is somewhere else. And the source gives this frequency. You can consider it roughly as a plane wave kind of thing. So this plane wave kind of thing will couple to the cavity over a very long length, right? And that is delta 2 delta x. And this 2 delta x is basically resolution. So how this is not giving the resolution of our sensitivity. The resolution of our sensitivity is very accurate, which is coming from the marker. Like we know exactly where it is positioned, and this is coming on the fiber. But if the source is far away from the fiber, the sound will. Okay, so we here take these frequencies quite accurately with different in terms of like these frequencies are like systematic ones. So what this is just noise, whatever frequencies available in your circuit. Yeah, this is we don't inject it. This is whatever comes in buildings, construction is happening, something else is happening. And we do not know what is the source of this frequency. So we detect it. Okay, now we compare our fiber-based acoustic sensor with all others. So these ones, the blue ones are all lab-based technique. That means they don't use any deployed fiber. So in the lab, they have isolated their systems from all sorts of noise and only see resolution of their fiber-based sensor. Whereas these green ones are deployed fiber. Our is also deployed fiber. We have a fiber going from here to here, building deployed fiber. And you see that we are doing very good compared to the global standard. And by the way, this has a resolution of 3 meter in position resolution, and we measured position resolution 5 feet. And this is a company, this is not a lab. Okay, so we are actually, and this is a very new result. We might actually do one better than this.
So lab should be better than company, right?
Yeah, we are
In general. No, in general. In principle, lab should be better.
So the difference between these things is like they are using a detector which has a sampling per second of megahertz. We have sampling per second of kilohertz. So if we can get a better detector, which is costly, that's why we cannot get, then we are sure that we'll be able to master it. That is the difference. Okay, why do we do these things? One important thing is actually active noise cancellations in the diode. That's why we started that. Why we should do this distributed acoustics? For any gravitational wave detector, this is like for like 4 kilometers, Einstein Telescope will be 10 kilometers, and others will be like 40 kilometers, and etc. Major problem is the seismic noise. And one of the things which is coming out for the next generation is, can we detect this seismic noise and give an active correction to the system so that we can isolate it. There is a group in Hanover, Maxwell, and they are also doing it for the light. So that is the thing why we want to do it. But there are several other applications like
You believe in finding. No, but in language it is different.
no, we have a separate fiber. Along the path of this arc, we have to have a fiber on the earth. And there are only
And you'll correct the photon in the tube.
so you have to correct it's environment what we have to correct this like hanging things here. Not
That's what I'm saying. Feedback will go from these fibers.
yes.
So you say the acoustic damping, but they also respond to vibration. So you cannot differentiate between vibrational coupling and acoustic coupling. Yes.
So in the ground we have deployed fiber. This is mostly vibrations. Right? You are not in the open environment where somebody is playing a loudspeaker and that one.
Yeah, but this acoustic sensing that's
We are since we can sense all these frequencies. That is like acoustic frequencies as we sense, we sense everything. But if it is deployed under the thing, then it is mostly connecting the system.
what we have here is open.
No, standard. Standard.
So quantum injection we are doing is all relational injections.
No. Because at the end it is coming to the lab, and there we take a 10-meter fiber and we put on the speaker and etc. And then how? That small part on the piston. Yeah, so there are many other applications like early warning of the natural calamity, underground deep sea surveillance, and structural health monitoring of the long overbridge or something like that, railway tracks, all these things. And importantly, geographical database for science and purpose. But our major interest is this one.
Whole mind,
Sorry?
whole mind. Mind. Basically,
Now, see, basically, now if I really want to give one RNP system, let's say like or any gravitational detector, I have to make everything pack and give it to them. Now everything is on the optics table and etc. So from that point of view, we use instrumentation to couple everything on a 19 single 19-inch rack. And there are a few things I already described. These few hardware, and log box, photon sink, and also this I did not discuss, but laser driver we have already developed. These are already developed and the features what you see. Other things we are developing the laser itself. We are also developing. An extended cavity diameter, the idea of interference filters we are developing it ourselves. And the cavity we have developed in the lab is a big cavity, but now for transportable thing, mounting has to be completely different. We are also designing the transportable cavity, which is a smaller, 10 centimeters. These two work are going on, and we call this system as reference photon dissemination system for yes. So these entire thing what you see, which is mostly electronics and laser systems, this is wavelength independent. Once you develop these things, only direct laser is a different thing, and optical things and etc. are different wavelengths for VRs and etc. Otherwise, electronics, optomechanics is wavelength. So once we get success into that, we basically want to use that knowledge to develop 205, which is the next generation of cryogenic light Voyager. Voyager is designed for 2050 and projected for 2050. It's a cryogenic thing. But we directly don't want to go to 2050 nanometer because, first of all, 2050 nanometer diamonds are heavily costly, and in the beginning, I'm sure with one of them, it makes no sense. 1550 nanometer has lots of applications, and we are also interested also about things like this. I believe 1550 nanometer is also projected for Einstein, so also useful for astronomy.
Okay. So for LIGO lasers, we don't need a about
No, I don't think so. Like I was
because
looking
the
into
interferometer follows the laser doesn't. The,
so laser, LIGO laser also have a reference current, and that is
at the end of the day,
Huh?
at the end of the day, the entire interferometer is what decides the frequency at which the laser should operate.
Yeah, so if you see for 42050 nanometer, you are saying that I don't need the reference cavity.
All you need is a stable laser
So then, please what?
that is tunable. This extra,
Yeah, you don't need.
what you have is not.
Yeah, it could be that you don't need. But we are developing this entire thing for 1550 nanometer because we want to do the acoustic sensing and all the others. And it's only not only for LIGO. Somebody says I want to only LIGO. Yeah. So I want to use only the photon thing. So these are modular things. Anybody can do whatever they want. Yeah, I am done. I got things. So what I told you, I discussed about we are developing the optical flaws. I mean, we have developed quite a bit of things, but there are things which are remaining to develop, and we're working on that. As an option, we have developed already a mechanism for distributed acoustic sensing. The required hardware infrastructure for that also we are developing. And this is something we have just started recently. This is very new. We're designing not this big ion trap, but now going to the cheap ion trap, but at least design that thing and then yeah. So together with another person in JNU, we have just started designing them. And the future is like, of course, in this entire block, mostly for the science students, we have to really go toward the active noise cancellation, how it happens. We have no idea at this moment. We are just, right now, we can only detect these acoustic frequencies or seismic frequencies and their position, but how to do the active connections, etc., we have to see, I don't know. We will complete these ones and maybe go to 205 nanometer, and we also want to make this cheap ion channel systems. Okay.
Yes, Vishnuji, for this very interesting talk, and we already have many questions, and Samosa is getting cold, so please, only few questions. Yeah, Sanjita.
See, this active noise cancellation part is completely different. It's for the Freudian noise. So, but on the other hand, I have another question about this. Was that about stabilizing what Suraj was asking at some point? Stabilizing the fiber itself. Since you can measure the vibrations using the phase delays, need you apply the same vibration on the fiber to stabilize it so that first of all that is incorrect because this is not only vibration. There are also temperature. Fibers are temperature sensitive and stress sensitive. So you cannot decouple all of them. That's true, but you are taking example. You are saying you are talking about phase stabilization of the fiber, about dash. No, I'm saying with the fiber, you are planning to measure ground vibrations. Yes. Which means that ground vibrations do have an effect on the fiber. Yes. The phase. Yes. So if you knew how to correct for the phase, then you could use the whole fiber as a reference cavity for you, right? I mean, you could use it's a very long reference. I'm asking that. I'm saying that if you knew how the vibrations are affecting your fiber, then you could feedback the opposite signature on the fibers to stabilize it. That is what we are doing. No, you are correcting the laser frequency. You are not changing the fiber. No, but in fiber, what do you change? How do you change length of the fiber? Not the length. It is the fiber because of the vibrations in the fiber. Yeah, you are observing a phase change, right? In the see, I need something to give a feedback. You have to actuate on something. I cannot stabilize the entire arc. No. I'm saying you would actuate right on the fiber itself. You could do this. later on.
So, well, I understand what problem will not be solved by just changing the frequency. You want to do a feedback so that that effect is removed from the bridging water.
Basically, you want
Then you instance,
the one for seven ratio, right?
it is not our problem. You guys should discuss to see how this kind really says is not our problem.
Right. I have a question regarding the time. So is it already yes, yes. So made of it's made of UL glass. Also expansion. This is a chronic glass, which is a special material from like US holds patents, and nobody else can take. Okay, so how do you write the meters onto the chemistry? Because the glue information pages. No, it's not glued. It's optical contact. There is no glue. It's optically contacted to this export. And there was force. It's coming. There is no glue. But machining wise, you made it so besides that it's glue is got aligned. There is no glue. There is like basically wise the surface roughness is 10 nanometer level, so that you can connect. You know, it's very similar to when you put this screen guard on the phone. This is like an optical. No, it's very similar. It's like very heavily polished surface. One of the mirror is curved mirror. It's not one of the mirrors. So that also is attached to this. Okay, yeah. So this mirror is like so like that. So this part is flat. Now the central part is flat, and this part is out.
Yeah, I'll come.
Sir, regarding the simulation, you have done the extra practice simulation also. 0%. Yes, yes. Sir, in Pune, it's a non-movable author, na? Like you're not transporting them. So, this lab-based chemistry, we are not. Why are doing the 0% temperature? That's because in Pune, we are not doing the zero temperature or go to zero. Zero crossing temperature means at a certain temperature, the thermal expansion coefficient is very low, like very close to zero. It's not zero temperature. It's zero crossing, like I just take it's from greater temperature to the positive. No, there is no negative. Everything is positive. At certain temperature, expansion coefficient is that's zero. Like water. It's not the temperature which is zero. Yeah, it's not temperature is.
A very light question. So with this active noise cancellation, can you create a music system with all this?
You can say both. We can want to read.
Okay, so let's thanks over the
Actively cancel questions.
I think how that's the correct answer as that's it. What that also has to be that stable. Otherwise, what is more phase effect. Basically, cavity system utilized to stabilize the laser that is used for the clock transmission. One of the components. One of the components. Instead of take additional. Let me show.